An MEA Regenerator was experiencing unexplained, severe corrosion causing numerous outages, downtime, and lost profits. My name is Simon Weiland, and I'm a Technical Applications Engineer with Optimized Gas Treating. Together, we will solve the case of the corroding regenerator. The unit is a conventional 17 weight percent MEA loop removing CO2 from the flue gas of a coal-fired power plant. The flue gas is 12 mole percent CO2 plus other gases as shown here. The recovered CO2 is intended to be used as food-grade gas for carbonating beverages. The regenerator has 4 reflux trays and 22 stripping trays. The design was for rich amine with a CO2 loading of 0.42 moles of CO2 per mole of MEA entering at 206 degrees Fahrenheit. The design reboiler steam flow was 38,500 pounds per hour of 50-pound steam, with the condenser at 105 degrees Fahrenheit. A digital twin of the regenerator was built in the ProTreat simulator. As designed, the regenerator temperature would be fairly hot throughout most of the column, with the CO2 loading steadily decreasing to around 0.17 moles of CO2 per mole of MEA. These are both fairly typical profiles for a properly operating regenerator. After a lengthy period of trouble-free operations, the unit unfortunately started to experience high corrosion rates, demanding repeated shutdowns to cut out and patch parts of the shell as they ultimately reached their code thickness limit. It's well known that oxygen will cause amine degradation, and since a power plant runs with excess air to ensure complete combustion, the CO2 recovery system included a solvent reclaiming skid to remove degradation products. The solvent was also laced with a filming-type corrosion inhibitor. The onset of severe corrosion was marked by the rich amine entering the regenerator at 192 degrees Fahrenheit, not 206 as intended by design. Further, the steam rate was only 35,400 pounds per hour, 8% below design. Thus, the stripping ratio was only 0.7 moles of water per mole of acid gas in the regenerator overhead, compared to the design value of 2.5. So, the rich amine feed was cold, the stripping steam flow was low, and the stripping ratio was extremely low. The simulation was repeated with the actual operating conditions, and the resulting temperature profile and CO2 loading profile for the regenerator clearly show the problem. The temperature profile is collapsed. Inadequate regenerator boil-up even caused the CO2 loading throughout most of the column to be well above the loading in the rich amine actually feeding the column. ProTreat's corrosion model predicted a corrosion rate of around 200 mils per year, bringing the regenerator to its corrosion limit within 6 months. This shows the inside of the column at one of the many shutdowns. The liquid level on the tray is clearly shown by the corrosion on the tray deck and sidewalls. The column wall within the frothy region appears to be very clean from the continual exposure of fresh metal. The wall in the vapor space is oxidized, probably from the result of oxygen in the vapor. In order to make a recommendation, a parametric study was performed to determine how the rich amine temperature affects the performance of the column. The green curve indicates the original design conditions, and the red curve indicates the operating conditions during severe corrosion episodes. These plots show that at rich feed temperatures below 200 degrees Fahrenheit, there is a sharp collapse of the temperature profile, which causes solvent loading to increase throughout much of the column. The recommended maximum loading for CO2 in an amine solvent of MEA is 0.4, and this is to prevent corrosion. The actual loading of 0.52, as seen by the red curve, is some 30% above the recommended maximum. This easily explains the severe corrosion. In summary, the combined lower feed preheat and reduced reboiler duty were the root cause of the problem. Feed temperatures below 200 degrees Fahrenheit are problematic for this plant, with the predicted corrosion rates in excess of 200 mils per year, allowing under 6 months of service life for the mild steel shell. Keeping the rich amine temperature above 200 degrees Fahrenheit greatly reduced the severity of the corrosion. Through the use of ProTreat's mass transfer rate model plus its corrosion model, the problem was quickly identified and a solution was put into practice. This saved hundreds of thousands of dollars in repeated unscheduled downtime, lost production, and unending maintenance costs. OGT's two main products are ProTreat and SulfurPro. ProTreat is a mass transfer rate-based process simulator, and it's unique in its ability to accurately model acid gas removal systems, as well as many other acid gas treating applications. SulfurPro is our rate-based sulfur recovery process simulator. It has state-of-the-art capabilities not found in any other software for accurately modeling the modified Claus sulfur recovery process. Fully flexible flow sheets allow simulations of any SRU configuration fully integrated into upstream and downstream gas processing operations. Together, these tools provide our customers with expertise in optimizing, troubleshooting, and designing units to minimize CapEx and OpEx in order to maximize profitability. We have a lot of great resources on our website at www.ogtrt.com, including numerous publications on gas treating and sulfur recovery, as well as tips and tricks to get the most out of the software. In addition to our software products, OGT offers consulting services. To learn more, visit our website where you can see actual additional case studies from our work. At OGT, we are working for a more sustainable environment through the use of simulation tools to optimize and troubleshoot your plants, while at the same time lowering your costs and maximizing profits. We can be reached by phone or internet as shown here. Thank you for watching, and I hope that this has given some insight as to how ProTreat and SulfurPro can help you get the most out of your process simulation and help in identifying sustainable operating parameters.